Okay, so today what we're going to do is we're going to take a look at the single displacement reactions and then also combustion. So if you'll open up your flip book and go to the single displacement tab, and then under the single displacement tab, we're going to be writing quite a bit of stuff, okay? So I actually put my activity series at the top right. If you wrote it at the bottom, if you glued it at the bottom, that's not a problem. Just make sure you understand like the size of the handwriting that's going to be required to fit all of these notes, okay? So what we're going to look at is first off the definition. So at any time you can pause or rewind this video. A single displacement reaction in general is going to be when an element reacts with a compound. And what that is going to make, okay, or what it will form is a new element and a new compound. Okay. So what you're going to need to have for single displacements is, in order to tell if the reaction occurs or not, you have to refer to the activity series. So what that is this little piece of paper that you have glued into your book. If you don't have one, there's an extra one over by my window. Okay, so we want to make sure that you note to yourself that you need the activity series to determine if the reaction will occur. Okay? All right. So the general form for this reaction, all right, is we need to have an element, so I'm just going to do a single letter, and we need a compound. So my element will react with my compound. Okay. So what I'm going to do here is, for this example, I am going to make this a cation, and if you look at my compound, then hopefully you can tell that this is a cation and that will be my anion. This is important because in a single displacement reaction, the like charged ions are what could be switching. Idea could, okay? It's all dependent upon the activity series. Okay, so in general, let's just assume that they did switch, then these like ions would switch places. So B would now be by itself, and then the A, since it's the cation, goes in front of the Y. Okay, just to make sure that you understand this idea of like ions, let's do another one where this time let's do X plus BY. This time, guess what the charge of my X is? That's right, he's going to be the anion, and then of course my compound. This time around, what would switch places is the like charges depending upon the activity series. So what you would look at is switching just the negative anions. So that means that Y would get kicked out, and then it would be B, the cation, with the X. Okay? All right. So let's now get into some real examples of this. All right, so let's just say, for example, okay, make sure you're getting all of these notes in your flip book, okay, is let's get some magnesium, and you've seen this before, it's a solid, okay, and let's react that with some hydrochloric acid, which is aqueous, okay. The first thing that you are going to do is you need to determine which ions might be competing to switch places. So what I'm going to do is I'm going to come down here and I'm going to ionize. So that'd be Mg with a 2+, and H+ with a Cl-. Okay. What we're looking at is I've got a cation that's free. So this is what's determining. The free element is going to determine who it's going to compete with. So right here, this magnesium, I need to check it out on the activity series. So check activity series to determine if they're going to switch. All right. So the way that the activity series works is it's kind of like a boxing match, which is where this cartoon comes in. So what's happening is that the more reactive, or maybe it's easier to think of it as stronger, elements are listed at the top, and the less reactive ones are listed at the bottom. So in this case, lithium, since it's at the top of the list, is way more reactive, stronger, able to kick gold out of a bond. This also applies over here to the halogens. These are going to be our common anions. Okay? So what we're going to do is we look back at our example. Notice that we're looking at Mg and H. So what you do is you go to the activity series and you look for your Mg. So Mg is going to be right there. And then you look for the location of H. I like this activity series because they've actually listed H as diatomic. Remember, it's diatomic. And so what we're looking at is, notice that Mg is clearly more reactive than the H. What this means is that Mg is stronger than the H. So it can actually kick the H out of this relationship. So what we're going to do is we're going to come over here and set the hydrogen by himself, and then we're going to put the magnesium with the chloride. Okay? Once we've got that, you can come back up and you can start making your ions. So I'm going to come up here. This is hydrogen, and when we go to do the chemical formula for hydrogen, you have to ask yourself, this is an element, it's sitting by itself, is it diatomic? Yes. So you put a little 2 there. Hydrogen, if you look at the periodic table, is red, which means that it's going to be a gas. Here we're going to crisscross and reduce, and I'll just tell you that that's going to be aqueous. Okay? All right, so what we're looking at here is that if you put these two reactants together, you should see evidence that a reaction is taking place by the bubbles. We're actually making a gas. Once you do that, make sure you go back and balance. Okay? So 1 Mg, 1 Mg, 1 H, 2 H's. So I need to make a 2. That means I've got 2 Cl's, 2 Cl's. So put a 1 in everywhere else. All right, let's take a look at another example. Okay? Let's take a look at gold. Gold, you've probably seen it before, it's solid. And let's put it in the same hydrochloric acid. Okay? So what you say to yourself is, you're like, oh, this is a single displacement. I can tell because it's an element reacting with a compound. As soon as you see that, you say to yourself, okay, I need to ionize these. So we're going to come down here. Now, gold is a transition metal on the periodic table. So we're just going to go grab its most common charge. And then let's just go ahead and ionize that. Okay. So what we're looking at here is, again, this is a cation. So if the element's a cation, you're going to compare that to the other cation. So check your activity series for reactivity to see if this will occur. If you look at the activity series, gold is way down here, and you got your hydrogen up there. In this case, hydrogen is higher on the list. It's more reactive, it's stronger than the Au. What this means is that this is not strong enough. The H was up higher, so the H is stronger than the Au. So the H cannot get kicked out of this relationship. So in other words, if you put these things together, you get no reaction. There's no gas, no evidence of anything. And that's your final answer. Now, I would like us to do one more example, okay? And this time what I'd like us to do is I'd like us to look at anions, okay? So let's take a look at, let's say you had some chlorine. Chlorine is by itself, so ask, is it diatomic? Yes, it is. On the periodic table, it's red, so I'm just going to list it as a gas. And we got some hydrobromic acid, and that's aqueous. So you say to yourself, well, gee, this is a single displacement because it's an element reacting with a compound. So I'm going to ionize. So you come down here. This is chlorine. That's a chloride ion. Do not drag the subscript with you. Subscripts really, in general, from what I can tell, seem to only go with the polyatomics. So don't drag this with you, okay? That's the chemical formula for chlorine. This is a chloride ion. Let's go ahead and ionize the hydrobromic acid. And now you can see that the free element is an anion, so we need to check that with the other anion, okay? So like charges can possibly switch. So what you do is you go over to your activity series, and this time what we're looking at is the chlorine is right here, right above the bromine. It doesn't matter that they're sitting right next to each other, it's the fact that he's right above them. That means that the chlorine is stronger than the bromine. So chlorine is going to kick bromine out of this relationship. So bromine's going to be by itself, and you're going to put the chlorine with the hydrogen. Once you've done that, you're going to come up and write a balanced reaction. Bromine. It's by itself. Is it a diatomic? Yes, it is. They've got it listed on the periodic table as blue, which means that we'll just go ahead and call it a liquid. And then crisscross and reduce my acid, and I'll just tell you that it's aqueous. Then you're just going to come through and you're going to balance everything. So if there's 2 chlorines, you need 2 of those, which means you need 2 of those, and everybody else gets a 1. That right there is going to be your single displacement reactions.